You should be good. Yep.
Hello, good morning. Have a homework due on Tuesday. So I was talking to one of you guys, and maybe whatever came out of that might be helpful for here. During COVID, I started recording this homework solutions, which I gathered was very useful in the earlier semester, or I got the impression that it was useful for students instead of going out there and having a different location. Anyway, you go and look into resources out there on the internet. So that was the idea of providing resources. But then I thought I will overuse it. I thought I will start teaching using solutions. So one of the things you will notice, or the complaints I have seen, or I think that is what is happening. You're getting overwhelmed with seeing the solutions. You are expecting that all these homework problems are hard, that is so much work involved, because that's a lot of math that I'm using. But what I've been trying to do is that I thought that might be useful is that I thought in the first 10 minutes of the solution, I'll teach you, because you're going to look into the solution more than my lecture. So, but that is firing back in the sense that you are looking at it and, oh, this is too hard. This is too hard a problem. I don't even want to go through the first 10 steps or first 10 minutes. So be careful in analyzing that. That's all. Probably it's an experiment I was doing. I wouldn't say experiment in the sense I didn't have any intention. My point was to teach something in the solution. But that might be a factor that might be playing in. So that's the impression I got while talking to one of you guys. Keep that in mind. I'm not saying anything good or bad about it, but sometimes it might be useful to someone who is really looking through the solution and spending 1 hour. It is good, but just be aware that I've been using solutions to teach also, instead of just giving, oh, this is a formula, do this, which might be only 3 steps, but I said, okay, this is an opportunity. I have full attention on the student, so teach, so which might not be the best thing to do, I guess. So be aware of that. That's all that's needed. Okay, hopefully that information might change a little bit. Any comments on that? That might help you if you want to. Okay, that's okay. Okay. We introduced the idea of electric potential energy, and from that point on, we said we would like to talk about electrical devices, very elementary electrical devices, but they are sufficient enough that with various permutations and combinations of the elementary devices we are going to be studying here, in principle, you should be able to understand most of what is there on the in any particular device. So it's an extremely powerful tool. Imagine it to be like your addition, subtraction, and multiplication, division in your mathematics. They are the most elementary operations, but most of the higher level operations can be thought of that, or at least if you don't know this, you will not be able to understand them. So it's they act like that. And the three electrical devices we talk about is capacitor. Second is a resistor, and the third is an inductor. Even though I'm listing them immediately, they will not show up in order in the next week or so. This will be spread out in in almost the whole semester, it will be, by the time you see detector, it might be 2 months or so. We need to study the whole of magnetism to use inductor, but resistance and capacitor will bring in now. So the main idea is that this understanding a capacitor allows you to think about storing charges. As you will know that everything we are dealing with deals with charges, positive and negative charges. You want to control them, and that itself is, if not anything, you should start thinking about how do you control them. You know that lightning involves a lot of charges. What if you want to really manipulate them? You want to control that a certain amount of charge should go in that corner of the room, and another set of charges should go on the other corner of the room. And there are many ways of doing it. There are two primary important ways. One is the geometry. You design the geometry of the room in such a way that all certain things happen on one corner and another thing happens in the other corner. So that's geometrical properties. By geometrical properties, I mean length, breadth, curvature, how much it is curved, and those quantities. That's what we mean by geometrical properties. And the second is material properties. And most often what we do in real life is use material properties because that gives us a lot more control on this, or has a lot more freedom. But it is, as far as analysis goes, it is much easier to work with geometry because geometrical parameters, we know how to do algebra with them. So you do analysis with geometrical properties, but then at some level, the hope is that we understand material properties in terms of the geometry, which is usually incomplete. There is a lot of modeling that goes in between in there. But nevertheless, I believe that if you can connect the material properties with the geometrical properties, that's good. But most of the time, there's a lot of error involved in that. But it helps you a lot, at least, to have a feel for what is happening. So we did introduce the idea of capacitance, capacitance of a capacitor. And that's of a capacitor. And we simply would like to have a symbol associated for this. We will start using them. So this is, as you notice, we have, when we introduce the idea of a capacitor, it's then two conducting plates, and you collect charges in there. This represents those conducting plates. This literally doesn't touch each other. You want to think of it like that. A capacitor is pretty much breaking a wire, and these are wires. So this is a symbol. This is a symbol for a capacitor. But you want to have in your mind that this is a conducting wire. Remember, a conducting wire means charges are completely free to go. For our purposes, they are completely free. Even when you're doing engineering or real life applications, they're completely free to go. There is no resistance you associate with a certain wire, unless you are doing some precision experiments. It is good to say that electric wires are perfectly conducting. This is also another connecting wire, and these are plates. These are conducting plates. How they are actually placed, how they are built, that won't be important for us. We will pretend that they are parallel plates, but usually they're rolled up. So you have a set of plate which is very flexible, and then you roll it into a cylinder. Sometimes it's spherical, sometimes you fill a liquid in it, sometimes you put a ceramic in it. So there are various ways of doing that. But for our purposes, we will imagine that there are two plates, and there is the area of the plates and the distance between the plates that will come in. So they will use the symbol C. So that is a capacitor, and then often we will write a letter C to represent the capacitance. And we would like to know what does C depend on? It depends on the area of the plates. proportional to the area of the plate. We're talking about how much charge can be stored in a capacitor. So maybe I should mention the one important one is that stores charges. And indirectly or directly stores energy. And we should know how does that change. Often there are other parameters involved. So keeping everything else constant, you can talk about what should happen to the capacitance or how much charge is stored if you change your capacitance, geometry of the capacitor. So that's way of asking a question, or you should ask how much the energy can it store. There is a lot of interest in the last 2 decades to come up with alternate forms of energy, and this concept plays an important role. This is that elementary concept. If you generate energy, you have to store it, and this concept immediately comes into picture. Because if you don't know those elementary definition of how you would store energy, then you get stuck in there. But that doesn't mean that this is the only thing. There are a lot of other factors considered. I was talking about what capacitance depends on. It depends on the area, proportional to area. If you give the more area, more charges you can place on them. So that's what is happening. It is inversely proportional to the distance between these plates. So maybe I can draw this again. So that's here. This is the distance B. And that is an area A. And it also depends on epsilon naught. So if it is made up of vacuum, it is epsilon naught. But let's, to be more precise, how can I say this? Let me remove the reference to the vacuum, the 0 in the subscript means it is vacuum. And now let me define this to be epsilon is kappa. That's not K, that's a kappa, that's the Greek letter kappa, and times epsilon naught. So this is, if it was vacuum, then kappa is 1. Anything more than, if you put in any material other than vacuum, that kappa becomes greater. And so kappa is equal to 1 for vacuum. Remember, vacuum is the best insulator you can have. And kappa is typically greater than 1 for materials. Not a vacuum, but materials. Like it can be even gas, like even air. It's not perfect vacuum. There's a little bit of amount of polarization in there, and that should be clear. So again, how do you control your capacitance? There is geometrical parameters A and B coming in, and there is epsilon A. This is for a parallel plate capacitor, and that is sufficient. If it was cylindrical or it is spherical, this expression changes a little bit. It becomes logarithmic, it becomes exponential, there is more rational features in there. But the broad idea is very much the same. More area, more charges, less distance, more capacitance it can, more charges it can store. So that's how we are going to work with it. That is also, as I said, we talk about potential differences. So there will be a relation. So this is your actual device property. Capacitance is the property of a device. You go to the market, and if you want to buy a capacitor, then you say that please give me a capacitor of 1 microfarad. Right? That's it. And but once you buy it, you cannot usually change that. That's a device. It's a fixed device. No, nothing you can change about that. Its capacitance is fixed. It's a geometry based thing. And once the geometry is decided, that's fixed. But what you can do with it is you can apply a voltage to that. So after that, what you do is you attach a capacitor Now it's symbolic representation. This is a wire attached to two parallel plates, but this is a symbol which means this is a wire attached to two plates as a capacitor. It doesn't mean that it is really parallel plates. It could be a spherical, cylindrical, and so on. What we do next is that even though we are going to be using this to store charges, we will use another device which already has a stored charge in it, and that is a battery. And so we will need another device to this, and that will be a battery, and that will be represented by this. So this now represents a battery. So this is slightly different symbol. This is a longer line, if you want, longer segment of line, and this is a smaller segment of line. This represents a battery. Again, for all your purposes, a battery looks like a cylinder, and it has a finite about 3 or 4 centimeter length. Sometimes it is smaller, sometimes it is bigger. You all know that there are positive and negative charges to a battery. So this represents that positive side of the battery. That represents the negative side of the battery. This two segments of line connected to that represents the wire. So you can connect it to something else. So this is a symbolic representation of a battery. So I took a battery, I took a capacitor, and an elementary circuit is you connect a battery to a capacitor, and you expect what will happen on the picture you're asking is what will happen to begin with. There is no charge on the capacitor. There is a lot of charges in a battery. In principle, both are very fundamentally the same, that both store charges, but you would like to know what is the difference. Very simplistically speaking, a battery releases its charges in a very controlled way, in a very long time. For example, you can keep a battery connected to a device, and even for 1 hour, it will keep working, and it will release its charges very slowly. Capacitor is extreme opposite. It will release almost immediately. Usually, the amount the time in which the capacitor releases its charges is less than a second. So typically, it's a millisecond. So whenever you want a lot of energy in a very short amount of time, you think of a capacitor. Whenever you want a lot of energy in a very long duration of time, then you think of a battery. So that's a very simplistic difference between them. So this is the battery, and the moment you provide the battery, this capacitor will start getting charged. In that sense, simplistically speaking, again, there is a positive, lot of negative and positive charges. You have connected a conductor. This is the wire. A conductor, in a conductor, a charge is free to move. Positive charges, there are a lot of positive charges. We show that to you like this. Lot of positive charges. They don't like each other. They like to stay away from each other, so they will start moving and they will come and collect in here. And negative charges come and collect in here. So that's negative charges and positive charges. And the question is, how much charge will come and collect in here? So plus Q in here, minus Q in there. And after a while, these start repelling further movement of charges, and the question is how much charges will come and collect in there. When it comes to a capacitor, its property is decided by C. When it comes to a battery, its property is decided by voltage V. So in each of these devices, you want to think of what is fixed. What is it that you cannot change once you have set up the circuit? In another circuit, you can change it. You can have different capacitors, but once you have selected a device and connected the wire, what you cannot change is C, and what you cannot change is V. For a battery, V is fixed. It is designed in such a way that the voltage is fixed, but the rate at which charges come out of the battery is a variable. You can change that, and the device or the circuit decides that. What does the circuit decide? How much charge will come at what rate? How many charges come out of this battery at what rate is decided by this circuit. This will decide how much charge will be placed on it, the maximum charge that will be placed on it. So those are the dynamics that happen. We start with the capacitor, the battery immediately charges will move in, and the question you ask is at what rate does the charge is moving and how much charge will be placed in it. So those are the questions you would like to ask. But for now, let's ask, suppose there is one capacitor, and I said these are elementary configurations. We would like to now learn how to make it complicated. How do you compound this effect? If you know addition of two numbers, how can we add three numbers? How can we add 10 numbers? Have to find rules for that. So similarly, now we have a capacitor. What if we have two capacitors? What if we have three capacitors? What if you put them in a certain manner, in a certain configuration? What changes? So let's talk about. Before that, I think I'm jumping. I need to say one point here that there is a capacitance C. The moment you attach a voltage, the property of the capacitor decides how much Q there is, and that's the expression we saw last time. So Q over Q over C, different ways of writing it. I suggest writing V on one side, and the expression for the device on the other side. Then I V is equal to Q over C. That's fine. So for a capacitor, the voltage across the capacitor, even though in this case it is trivial, the voltage across the capacitor is the same as the voltage across the battery. So again, I should repeat this a little bit. Notice when I say voltage, it is the difference in the voltage that's important. It is when you go from here, negative charge, if it was a positive charge, from here to there, you're going to a higher potential. Again, remember your battery or the capacitor, these are positive charges, these are negative charges. If a positive charge has to go from here to there, it has to climb a potential. It is like climbing a mountain in gravity. It would prefer to stay close to a negative charge, but you're pushing it away, so that's a potential, higher potential. So positive charges or positive plate in a circuit is always at a higher potential. So lower potential, higher potential, you will say there is a potential difference of V. Notice the language, even though you typically say this battery is voltage V, what is important is that the potential difference between these 2 points is V. This could be 30 volts and this could be 10 volts. That leads to 20 volts potential difference. Or you can say this is 20 volts and this is 0 volts. That's also a potential difference of 20 volts. So it does not matter what point it is the reference that matters. And often, sometimes in electrical engineering or in many of the circuits, you will ground them. So if ground becomes a reference, and by that you're saying that the origin is the earth, and that you're setting it as 0. So if you decide to set this point as 0 or this point as 0, then related to that, this is plus the voltage. Then you come in here, since this is the wire connected conductor, everywhere on a conductor, voltage is the same. There is no potential difference between any 2 points in a conductor. That will be a quiz question or an exam question. What is that? So I give you a conductor in the shape of a torus, and I give you 2 points on the torus, and I ask you what is the potential difference between them. Doesn't matter what the geometry is. If it's a conductor, potential difference between any 2 points in a conductor is 0. Potential difference, there might be a potential at one point, but potential difference is 0. It's like whatever we talked about, electric field is 0. So the potential difference, electric field is a change in potential difference with respect to a certain amount of distance. So the potential difference between this point and this point is 0 because it's the same wire. That's a concept. And I can give any complicated circuit, and for example, you could have any complicated circuit so that some device, from that some device here, I connect a device there. So that becomes complicated enough. And let's say I connect it from here to there. And this is the battery, and I say this is a plus 10 volt here. And you say that what's the potential difference between these all these lines that are floating around? They are conducting wire. What's the potential difference between point A and point B? It seems that it's very tempting to say that's a battery that's 10 volts, but it's not because it is connected. Right? I've started the battery, so immediately you have a wire connected. It is no more 10 volts, it is 0. Right? So that is a difference. So that is a, that's why it's called it's a short, because from here to there, there's a plus 10 volt, but here to there it is 0. That's inconsistent, so the nature doesn't like it. So it will basically discharge the whole battery as quickly as it can. So there'll be a lot of current that are flowing here, and very immediately this plus 10 volt will disappear. Is that clear what I mean? So the point I'm trying to convey is that any two wires that you see around, from this point to this point, it's 0. That will be as a concept we need for circuits. And the two equations you need, this and this piece here. Once you have selected the device, you don't need this anymore. So once you're working with circuit, this becomes your most fundamental thing. What does P depend on? It depends on geometry and material properties. But once you have used it inside a device or inside a circuit, then you don't have a choice. So C is just a constant. So C is a constant. B is a constant in the sense we get a battery and connect it. What you're asking in a capacitor problem is what is the charge? B is decided, C is decided. You're asking what is the charge? That's the dynamics. That's what the system will do. So how much is the charge that can be stored in that capacitor? So that's a simple question we ask. For one capacitor, that's immediate. It is you just multiply these two numbers, right? Q is equal to C times Q. But now we want to compound this. We want to actually put in 2 capacitors, 3 capacitors, and we will see that it's slightly, we need some logical arguments as to how they add up. What is the concept behind that? So let's look at that. So let's talk about capacitors. In series. So what does, and we'll start with 2 capacitors in series, then we will talk about 2 capacitors in parallel, and immediately with those concepts you should be able to do 10 capacitors, some of them in series, some of them in parallel. It gets compounded very quickly. So let's, so when I say this, what it means is that you have taken 2 capacitors like this and connected one after the other, like in a series, right? So one end of the capacitor is connected to the other end. We will talk about capacitors in parallel, which will be slightly different from it. And you connect them to a battery. And you don't have to choose these capacitors or capacitors to have the same capacitance. So what is fixed is C1 is known, C2 is known. Let's say for if it has to have numbers in front of you, so let's say 1.0 microcoulomb. This is 2.0 microcoulomb. Remember, microcoulomb is relatively large. In normal capacitors that you get in the market, microcoulomb is the larger side of the capacitor. Nanocoulomb. Oh, what is the mistake there? Farad, yeah, thank you. So nanofarad, microfarad. And that was not intentional, my mistake. Microfarad and nanofarad. Typically, microfarad is a larger capacitor, or high-end capacitor, and nanofarad is very easy. So nanofarad can be made with ceramics and paper. Microfarad capacitors, you need to put in some liquid to get those effects very large. So you treat them in the shape of a cylinder. So you put in some acid and so on. Okay. So that's C1 and C2. So that's given to you. And this is the battery. So that's the voltage V. And let's say that's 10 volts. Typically, you get 9-volt batteries or a 12-volt battery, but just for algebra purposes, let's keep it 10. So typically, the market, you get a 9-volt battery is more common. But if you're in a lab, you can actually control it very easily. There's a knob, and 10 volt is very much fine. These units are volts. So if I agree, that's a little confusing, so let's write volts. But I'll somehow write just the steps. And the goal is to find out, like, so this is all fixed now. The moment you design a circuit, this is all pre-fixed. Even if the numbers are changing, these three are fixed. And your goal is to find out what is Q1, how much charge and comes and collects in here, and how much charge comes and collects in the second charge. That's the simple question we are asking. And the geometry decides that, or geometry in the sense the geometry of the circuit decides that. So how do we know what to look for? So there are two equations you want to talk about. One is immediately the voltage. Always, if I said it is always the potential difference that matters, the potential difference between these 2 points, there are 2 ways to measure this. I can go this way, or I can go that way. And the potential difference has to be the same all the time. Between any 2 points, it has to be the same. And let me say this is A, and that's B. And yeah, that's B. And let's say this is point C, and that's point D. So the potential difference between B and A, VB minus VA. So let me say true. So this should not depend on it, but for simplicity, I'm saying true point C. If I calculate it through point C, that's just a concept. When you start doing the homework, you won't need this elaboration in there, right? So that's equal to. So I'm going through this point, and reaching here, I have crossed the voltage V. So this difference is only just 10 volts. So this is positive, higher potential, lower potential. That's just V. That's it. So this is the same at this point. That's the same at this point. The difference, potential difference across the battery is voltage V. And it matters which is higher and which is lower. You would say VB minus VA is plus V. VA minus VB is minus V. The plus and minus matters. Right? So that's your potential difference. And the same thing you do from the other point. So let's do VB minus VA through point D. Seems like I'm taking a longer route, but that's a concept. But as you proceed, this will be immediate. Like within one step, you should be able to write an equation. That will be our goal. From when you're going from here, you're first encountering this capacitor, and this is positively charged. So this will collect positive charges here. This will collect negative charges here. We go from positive to negative, and again, if this is negative, that's positive. It seems like positive to negative, then again positive to negative. So there are few potentials, but each of them have voltage V. So let's say this is voltage. So this is notice when I'm doing voltages, it shows in parentheses that means it's the potential difference across the capacitor. So let's say that's V1, and that's V2. So that's V1 plus V2, but V1 is Q1 over C1. So notice I'm jumping a step here. That's Q1 over C1 plus Q2 over C2. This means that this is V1 and that's V2. So I've got an equation now. Notice these two are the same. Forget this. This was just for detail that I wrote how you come across this equation I'm writing. So I have Q1 over C1 plus Q2 over C2 is equal to voltage V, which will read as, so this is Q1 over, if you allow me to not write the microcoulomb, that's sorry. Okay, I'll not write it. That's wrong. If you do this in the homework, I take off points. I'm allowed. Sorry. I think it's more, it helps probably to do this. If I put it, it's more clutter. Is that okay? Okay. Micro. Better. Yeah. But then there's a variable. Let's turn into 10 raised to minus 6. So there's the three numbers given. What I want to emphasize here is that all the numbers are given, but there are two unknowns. Q1 and Q2 is an unknown. Make it very clear. Numbers known in the circuit, Q1 and Q2, I don't know, but I have only one equation. Q1 on one equation, it doesn't help much, right? I cannot solve it. Or the nature doesn't know how much charge how to decide how much charge is to give to C1 and how much charge to give to Q2. So this is not sufficient information for the nature to decide what it should do. So that we need to find another constraint which depends on a natural process that the nature uses. Notice again, the only thing we use is potential difference between these two has to be the same, whether I go this way or that way, and that puts a constraint on the nature that it has to satisfy this, so it has to satisfy that equation. So, but now that's not enough information. So let's go back and ask this piece here. And notice this is a conductor, right? This is a conductor, this is connected. Physically, this piece is not connected to anything. Let me, the dotted line I'm drawing. Everything inside this dotted line has no way of accessing this battery, charges in this battery. So to begin with, that was a neutral piece of conductor. It has to remain a neutral piece of conductor. Is that clear, that argument? This was to begin with neutral. There was no charge on either of the capacitor. Whatever you do here, it has come from this battery, that has to stay on that side of the capacitor. This side has to come up because there is full positive and negative. So this has to remain neutral. This side has minus Q1. That side has plus Q2. But I said they're neutral, so they have to add up to 0. So you have come up with a new constraint now. Q1 plus Q2. We're talking about the magnitude, right? So that's a positive, and that's positive. So Q1 has to equal to Q2. That's what I want to say, because it's a positive charge that I'm comparing, right? So that's plus Q1 here and plus Q2 here. Those are the two quantities I'm comparing, not this. Q1 is negative of Q2 is not the correct answer. It is positive charge. So be careful of what I'm writing here. So Q1 has to be equal to Q2. Is that clear what I said? Another way of looking at it is how much ever charge plus Q1 is pulled in here, the same amount of charge has to be pulled on the other side. because it's the same battery is releasing the charge, it remains neutral, otherwise there will be instability. So you come up with the same amount of charge, but be careful, I think I might have confused you with whether it is positive or negative. It is the charge on the positive plate, our charge on the positive plate that we are comparing. The variable Q1 is the charge on the positive plate. So this one was the charge on the negative plate, but I want to talk about the charge on the positive plate. So that's Q1 is equal to Q2. So two constraints, I did not put in that constraint. If I use conductor, the property of the conductors decides that. That means nature doesn't have a choice. They have to obey these two rules, and that is sufficient. Once you get these two equations, that's a mathematical problem now. Two equations, two unknowns, I can solve for them. And that's easy because now you have set Q1 is equal to Q2, and you have Q1 plus over 1.0 plus Q2 over 2.0 is not, what did I do? Q1, I meant right, Q1. Q1 is equal to 10, 1 plus 2, right? So this is Q1 times 2 plus 1, 3 over 2 is equal to 10. And that gives me Q1 is equal to 20 divided by 3. So that's 6.666. But two significant digits, that's 6.7. But I could not forget those micros that I forget I purposefully draw. If you are not allowed to, that is for illustration purposes that I was dropping. So put in that micro here. I should always have kept that there, micro. And then what happens? There is a micro. We add these micros, and here and there are two micros here, yeah. So there's two micros, right? So micro square, get that out. So when you take it on the other side, this is micro, and you will bring back a unit system coulomb, right? Volt over farad is a coulomb. So you get 6.7 micro coulomb. Question, I confused here. Yes, please. Oh, you raised your hand. Okay. Is that, did I confuse here? Did I go over this again? Yes. Okay. So it was Q1 over C1 plus Q2 over C2 was equal to V. First of all, Q2 is equal to Q1. So I can replace that. So Q1 over 1.0 allow me to write micro. Okay, so that's okay. Plus Q1 over 2.0 micro is equal to 10. Pull the Q1 out, and that's pull the micro also. How about that? Micro also out. That's 1 over 1.0 plus 1 over 2.0, and that's equal to 10. This is 10 raised to minus 6, remember? 10 raised to minus 6. 1 plus 1 over 2, that's 3 over 2. 3/2, but Q1 over 10 raised to minus 6 and 3 over half. If it helps, it is actually should be written in 2 digits, but if it helps you, you'll see that you are through, so that's 3 over 2. And that's what it is. And Q1 numerically then is 2 over 3 times 10 times 10 raised to minus 6. So that's 20 over 3. This is 6.7 into 10 raised to minus 6. At this point, you'll bring back the units. Charge is measured in coulombs. As far as your SI units, you can drop all the units and bring back. If you're consistent that you keep all the units correctly, then you don't have to write the units all the time. And that's coulomb. and replace this 10 raised to minus 6 again. That's my equivalent. Sorry. But that's mostly algebra, same algebra that we have used in many other places. The few concepts that went in there is that the potential difference between any two points in a circuit is the same however you reach that. If there is a circuit that has 3 loops, all 3 loops have to give you that. Each of the loops will give you a new condition. And we will later on use that, and that will become a law, which is called the Kirchhoff's law. So we have used some law here, but that's not really a law. I mean, it is raw in the sense that potential difference between any 2 points has to be the same. However, you reach that. If you reach the mountain, the gravitational potential energy, whether you reach that mountain after going to another galaxy and coming down the same as directly going climbing the mountain within 10 feet or something. So that's the idea for capacitor. Often you want to associate one capacitance value to this. That's okay, but now you say that okay, then it's 2 capacitors. I've added for some purposes. It was useful to think of it as 2 capacitors, but then you have an electrical circuit that's not space enough to connect 2 capacitors. That's just a story I'm cooking up to point the fact that you can replace this capacitor with a single capacitor that does the same job. Right? So what is the job the system is doing? It has pulled some charges from the battery. How much charge did it pull? Q1. It's the same amount of charge on both sides, like Q1 and Q2. So the only thing that has happened as far as the whole capacitor set, if you talk about, is that something was connected, it pulled in some amount of charge. And then you ask the question, can I get the same job done using a single capacitor? So this is the idea of an equivalent capacitor. You want to connect a single capacitor that's the same job as that 2 capacitors. So that's C equivalent now. EQ stands for equivalent. And notice this is conceptually different. Earlier we were saying C1 and C2 is given and charge is the unknown. But now I'm flipping the problem. I want to find out what is the capacitance of the capacitor that I should know and go and buy from the market, so that instead of 2, I'm using only 1 charge. It's like, say, if you have 2 electric bulbs, I want the same effect, which is how much light there is in the room, or I want to replace those 2 bulbs with a single bulb and have exactly the same effect. So here, the effect is that charge, right? And it is Q1. How much charge will be collected on that? It's the same in a series circuit. That's what it is, and the voltage is V. So C equivalent now is, remember, Q over C is always voltage, right? But this time I'm going to write it for C. So C equivalent will be Q over the voltage V, where Q is equal to Q1 or Q2, either one of them. And it's the same charge that was collected on both. So it is either Q1 or Q2, and you replace that. So we already calculated this on 6.7, but 6.7 microcoulomb divided by 10. So that's 10 volts. So that's 0.67 microfarad. I wrote it for numbers, but it is good to think of this in general, right? So this was for a specific problem. So let's do this, and C equivalent is equal to yeah, so what we want to do is go to this equation, Q1 over C1 plus Q2 over C2. It was a defining equation for series circuit, was equal to voltage V. But voltage V is also equal to C over Q over C equivalent. Also equal to Q over C equivalent. This was the actual circuit. This is an abstract circuit that we are building, right? We are saying what is the equivalent circuit that does the same job, and Q is the same as Q1 or Q2. And so this is equal to Q1, which is also equal to Q2. So since all of them are the same, I can cancel out the charges and say this is 1 over C1 plus 1 over C2 is equal to 1 over C equivalent. So if you want to find out how much is that equivalent circuit, we did this for a very particular problem, but I didn't even have to calculate the charges. I could have done it immediately. Then I would have said this is 1.1 over 1.0 plus 1 over 2.0 in microfarad. This is 1 over C equivalent. This is, remember, this is the inverse of that. So remember to flip the answer at the end. This is equal to 3 by 2. But I'll flip it. If I get the C equivalent, I need to flip it. C equivalent is 2 by 3, 2.0 over 3.0 microfarad, which is exactly 0.7. In all, there are 3 equations you should be comfortable with using for a capacitors in series. That's 1, that's 2, and that's 3. In principle, 2 is sufficient. Any 2 of this is sufficient, but mostly these 2 because that's the dynamical part in that. Any questions on this? Like you'll be building more complicated circuits using this, so that will be your elementary construction. And hopefully, as if I understand correct, at least some of you might have seen this in other courses, so it should not be completely brand new. So that's like sort of a review. Okay, so that's capacitors in series. So we can, there are other ways of assembling 2 capacitors. And the other is capacitors in parallel. Is there any other configuration you can attach to capacitors? Only 2 capacitors other than series and parallel? Probably not, but I'm not sure. So, capacitors in parallel means 2 capacitors like this, and another capacitor put it here, but this time we connect them same side, connected together. And the 2 is connected to a battery. Again, this is C1. One thing, remember that what we did a minute or 2 ago, capacitors in series, when you added them, What was the equivalent capacitor we got, if you remember? Just now what we calculated, C equivalent, how much was that? 0.67, I think, correct? That is less than either one of them. You had two capacitors, in series, the third capacitor will always be smaller than the smallest. Okay, so that's always a general rule that you will see, and here it will be the opposite. So keep that in mind, that will help you as a concept later. So let's say this is again 1.0, just so that we can have a reference to keep the same capacitor, microfarad, and that C2 is 2.0 microfarad, and let's have the voltage as 10 volts. Or Q, say this. Again, the problem is the same. How much charge collects in here? Q1, and how much charge collects on the second capacitor. Earlier it came out to be exactly the same, but it doesn't have to be the same in this case. But what we did there was the voltage difference, potential difference between point A, let's say this is point A, and that's point B. Usually these are connected across the battery, but now to go from point A to B, there are three ways of going. I can go through point A, B through C. I can go to point A to B through D, and another point is E. Right? All three must be the same. Okay? If I go from BA minus BB through C, right? The B through C, that equal to plus B. I can do the same thing, BA to BB, and why should this be the same? Because these are all connected, right? Anywhere on this is the same. So BA minus BB through, let's say, D is equal to, now I'm going through the capacitor. Let's first go to C1, so that's 1 coming from, right? The voltage difference across the capacitor is Q1 over C1, Q1 over C1. And for the same thing you do through E, right? That's equal to Q2 over C2. All of them are the same, so you immediately say that V is equal to Q1 over C1 is equal to Q2 over C2. That's actually two equations, right? Let me write them as two equations because there are two unknowns that we need to, let me write that as V is equal to Q2 over C2. That's a better way of saying that, because now we have two equations, two unknowns. I can solve for Q1 and Q2. Like the nature is completely determined by these two equations. Starters are determined. So Q1 here. So let's put it. So 10 volts is equal to Q1 over 1.0 microcoulomb. That immediately tells me that Q1 is 1 is equal to 1. Sorry, farad. 1.0 microfarad. Sorry. This is 10 volt again, that's equal to Q2 over 2.0 microfarad. And Q2 comes out to be equal to 2.0 microcoulomb. And it's wrong, right? That's 1 into 10 is 10. That's 10. Sorry. 2 into 10 is. Is there any other mistake? Okay, so let's immediately notice in series circuit, charges are the same. So typically what you say is that in series, charges remain the same, voltage distributes. Voltage V1 plus V2 is equal to V. Voltage distributes, charges remain the same. Here, voltage remains the same, charges distribute. Charge distributes, voltage remains the same in parallel. It's the opposite in the other configuration. Next, once you have this, so let's get two equations, you can also build an equivalent circuit. So now we do the same thing. Here, so we have to have a single capacitor that does the job of two capacitors. But if you think of these two as the same, what is it doing? Some charge was pulled by capacitor C2, some was pulled by capacitor C1. As a whole, it has pulled a charge of Q1 plus Q2. So the question you're asking is, which capacitor will pull a total charge of Q1 plus Q2? Right? Notice the concept here that I'm pulling in Q1 plus Q2. Why? Because some of the charge goes here, some of them go there. So I have to ask which capacitor will pull a charge of Q1 plus Q2, and that will be defined as my C equivalent, and the same would be V. And you would say that C equivalent or Q1 plus Q2 is C equivalent times V. But Q1 plus Q2, I can replace it from here. So Q1 is C1 times V. Q2 is C2 times V. That's equivalent of that's equal to C equivalent times V. Voltage cancels out. Remember, voltage remains the same in parallel. It's the charge that distributes. So we have C1 plus C2 is equal to C equivalent. Eventually, the algebra that we do with this comes out to be reasonably straightforward. And I've noticed that in the exams, most of the students do well in this. So try to master the skill. This is if you did, or on an average, I felt that first exam came out to be harder. So this is a place where you can make up. So this comes out to be easier. So try to do well in this. Now that we have capacitors in series and capacitors in parallel, you can immediately go and do more complicated circuits. I can make 7 different capacitors, and then the standard question that you ask is what is the equivalent capacitor? Right, that's an immediate thing you can ask. So let me very quickly do an example where you see at least 4 of them. But you can easily make it 10, 20. So let's start. Let's see. That's capacitor here. And let's say 5 of them. So this is 1.0 microfarad, the P1, P2, P3, P4, and 5. Let's say, if it makes sense, Pn is n microfarad. Is that okay? Okay. It's, I'm afraid that it might be confusing. So it's 1.0 microfarad. 2 is 2.0 microfarad. C3 is 3.0 microfarad. C4 is 4.0 microfarad, and C5 is 5.0 microfarad. So better not to be lazy. So that's not relevant. That's just the notation. And the question is, what is the equivalent? Of course, we can ask what is the charges on each one of them. It's a little more work, tedious work, but after I have done what I did for the last few cases, you can ask what is the charges. But that's a little tedious because there's a lot of work there. But C equivalent is much easier. So identify which one of them is in parallel and which one of them is in series. Usually, this is, for example, C1 and C2 are not in series. They are not in parallel either. So you usually you have to break one at a time. So the only thing that you can break here or compress into is that these two is in series. So you go ahead and draw a new diagram. So that's C1, that's C2. That's C3. And now instead of the last two, I say that this is 4, 5, so that is C6. Where C6 now, these two are in series, so I use the parallel configuration, right? So C6 is equal to 1 over C4 plus 1 over C5. It was 1 over 4 plus 1 over 5. And that is 5 plus 4. 9 divided by 5 into 4, so that's 20. So that C6 is equal to 20 over 9, which is about 1.1, 1.1 and so on, right? So let me write it like that. This microfarad. That's C6 now. But now the moment I do this, I have C6 and C2 parallel. And you can do this is P1. Now these two are in parallel, so let me call that P7. And this is C3. And C7 now, parallel, they just add up, right? 7 is equal to P2 plus C6, that's 2.0. Plus 20 over 9. 9 to 18 plus 20, so that's 28 over 9. So that's about 4.2 to 2, I suppose. Microfarad. 4.2. Right. So that's C7. And after this, these two are all in series, right? This attaches to this state and so on. So these are all in series now. So I can replace it with a single capacitor. So that's C equivalent. And C equivalent finally is equal to C1 plus C7 plus C3. That's 1.0 plus 7 was 78 over 9 plus C3 was 3. So 3 plus 1, 4, 4 into 9, 36. So that's 74 over 9. Is that correct? Correct me if I'm making a mistake. So that's 9 into, okay, 81 is 9. So 7 into 8, right? So 8.2 microfarad.
It's in series and not in parallel.
Ah, good one. Sorry. Bad dish. Thank you. Thank you very much. Yeah, so okay, so again, so it's in series, not in parallel, 1 over the equivalent. Thank you very much. That's 1 over 1.0 plus 1 over, let me write that first. 1 over C1 plus 1 over C7 plus 1 over C3. And that's equal to 1 over 1.0 plus C7. C7 is 38 over 9, so that's 38. 38 over 9 plus C3, that's 1 over 3. Okay, it's a little harder. So, help me. So 38 into 3, right? That's what you would do. So let's say this is 38 plus 9 into 3 plus 38, I suppose. Divided by the phosphorus. And don't forget invert it. This is 1 over C equivalent. And invert it. So you say 38 into 4 plus 27. So not C equivalent, so this is 1 over C equivalent. But I'm doing equivalent is equal to 0.63. Four. Is that what you guys heard? No. Okay. Did anyone get this? No. Okay. Let me check it. So that
Yeah.
okay.
That's great. I got that.
Get someone got that?
Yeah.
Okay, so C equivalent is equal to 114 divided by 179. And hopefully. Yeah, 0.64. That's all. Thank you. Okay.